Hello. So, as there we go. As Tristan said, my name is Iribarren. I work at CERN in the IT department. That's my day job. I'm in charge of the Linux infrastructure service. We provide the packaging, the software distribution for the Linux operating systems that we support at CERN. And I'm also in charge of the private cloud that we have, where that basically underpins all of our infrastructure. That's based on OpenStack. So those are the two CERN hats that I wear. And I'm also a member of the board of directors of the AlmaLinux OS Foundation. So today I'm going to talk to you mostly about CERN. So for those of you that don't know, CERN is the world's biggest particle accelerator and laboratory. It is located in Geneva in the Swiss-French border. So I don't know if you can see here the red line. That's the border. This is the airport in Geneva. What you see drawn here is our largest machine, which is the Large Hadron Collider. It's obviously underground. People generally do not like to have a particle accelerator through their living rooms. We have four main experiments: CMS, Atlas, LHCb, and ALICE. I'll talk about those a bit later. And our goal is basically to understand the most fundamental particles and laws of the universe. As goals go, it's not that bad. So how do we do it? We build the largest machines to study the smallest particles in the universe. So we develop technologies to advance the limits of what is possible, and we perform world-class research in theoretical and experimental particle physics. So for this, we basically have three main pillars of technologies and that we work with. The first is accelerators, second is detectors, and the last one is computing. So first I will go a bit into accelerators. So at CERN, we are very lucky because we have a very flexible accelerator complex. We've been at this for a while, and every time we build an accelerator, we make sure it's connected to all the previous accelerators. And that gives us a lot of options of producing different types of particles, doing different types of experiments with them, and generally opens a lot of doors for us because we can also tailor the new accelerators that we're building to specific energy ranges so that it optimizes everything. So I can tell you a bit about the life of a proton that is about to get collided in one of the detectors. So the protons will start in a large hydrogen bottle at the beginning of LINAC 4. The hydrogen atoms are, the electrons are removed from the hydrogen atoms, and then the protons are injected into LINAC 4, which is a linear accelerator, and then they start getting accelerated there. In the LINAC 4, when they get out the other side, they reach 52% of the speed of light. And then from there, they get injected into the booster, where they are accelerated some more. And there they reach 91.6% the speed of light. From there, they go into the proton synchrotron. There they go to 99.93% the speed of light. There they move on to the SPS, 99.9998% of the speed of light. And then finally, LHC, 99.999, you get it. As you can see, it is progressively more difficult to get closer and closer to the speed of light. It takes a lot more energy. The machines are a lot bigger because you just need to spend a lot of energy to turn the protons around, make sure they complete the circle. Otherwise, you lose them out the sides. You can also see from this picture, you have the dates of when the different accelerators were built. The PS is from 1959, so it's a really old machine. These are not the kind of things that you generally throw out. You build them. If they continue to work, you upgrade them, you keep using them because they're really expensive and it's good to have a lot of accelerators around. We also, since all of the machines are interconnected, we can do lots of interesting things. So for example, protons accelerate PS, and then from here we can turn them into antiprotons and then do experiments with them in the antimatter factory. Just yesterday, CERN announced that they managed to transport antimatter in a truck from one part of the CERN site to another. This was something that was done by one of the experiments in the antimatter factory, and it's pretty interesting. The final plan for that is to be able to produce antiparticles in the accelerator and then transport them to a research lab in Germany where they want to do some other tests with them. So that's never been done before until yesterday. Then, well, we also have different areas where we can shoot particles and do different types of experiments. Generally, this is where we test electronics and new detector technologies and things like this. So this is all possible thanks to the fact that we have a very interconnected accelerator complex. So the Large Hadron Collider that I mentioned before, it's 27 kilometers in circumference. It's 100 meters underground. It is a very, very complicated machine. It has more than 9,000 magnets of 50 different types. The biggest magnets are the ones that you see here in the picture. We have 1,232 superconducting dipole magnets. The job of these magnets is to steer the particles around the beam, around the circle. The magnet part is just the little yellow things you see here. So these are the beam pipes. We have two beams that are going in opposite directions in the ring, and then they cross in the detector cavities, the interaction points as we call them. And so all of the steering is done by these big blue magnets, 15 meters long, 35 tons. So it's very big hardware. We also like to say that CERN is the coolest place on Earth. We run the world's largest cryogenic system, and we actually keep it at a temperature that's colder than outer space. It's at 1.9 Kelvin, which is minus 271 degrees Celsius, so it's not bad. We do this with 120 tons of helium, and we use all this helium to cool 35 tons of equipment, so that's all the inner magnets. We use so much helium that the helium market moves when we are going to buy stuff. And it's actually worse than that. The helium manufacturers have realized that the LHC schedule is public, so they know when we're going to buy stuff. And then they jack up the price. Yeah, it's really nasty. So we have four main detectors. These are the four ones that I mentioned around the interaction points. We have Atlas, which is the biggest detector. CMS. Is clicking up? No. CMS, which is the heaviest detector. It's the compact muon solenoid. These two detectors are general purpose detectors. They both are complementary to each other. They can measure a whole range of different types of physics, more or less the same things that the other ones can see. And this is not duplication, it was done on purpose because you have no other scientific facility of this kind anywhere else in the world. So if you only have one detector and you publish a result, who's going to verify that it's true? So this is why we have two different detectors that both look at the same stuff. We can't announce any sort of results unless both detectors agree and they both see the same thing. So they're basically checking each other's work. Then we have ALICE. ALICE is focused on heavy ion physics. For a month or so out of the year, instead of protons, we circulate lead ions and we collide those. ALICE is really interested in those kind of collisions. And then we have LHCb, which is structured very differently from the other detectors. The other detectors are all kind of like a barrel. LHC is like a bunch of panels. And LHCb is focused on B quark physics. They investigate the differences between antimatter and matter because during the Big Bang, supposedly there was 50% of each. When matter meets antimatter, they annihilate. But somehow we are all matter and there's barely any antimatter left. So there must be something different between the two that we don't know about yet. So this is one of the things that LHCb is working on. Now, one interesting thing to mention here is that all of these experiments are completely separate collaborations from CERN. So CERN is like we provide the accelerators and some of the basic infrastructure. The Atlas collaboration is 6,100 people that work on the Atlas detector and nothing else. Then you have another 6,000 or so for CMS, and then Alice and LHCb are smaller, about 2,000 each. But these are separate legal entities. They use CERN infrastructure. They are research physicists from universities, but they are not actually employees of CERN or anything like this. They go there and build their detector around our accelerator. There we go. So detectors are like giant 3D cameras, basically. Their job is to measure the energy, the direction, and the charge of new particles that are formed in the center when there's a collision. The detectors are massively complicated. They are generally divided into sub-detectors for different kinds of particles. You could think of them basically like an onion. So you will have an inner core of like super sensitive detection equipment for a specific type of particle, then an outer layer for particles that get through that first layer without being destroyed, and so on. So they have a lot of, okay, not moving parts because you want them to be always in the same place, but they have a lot of components. We have, so for example, these numbers are for the Atlas detector, which is the one in the picture. 100 million individual data points per event. So event is one intersection of particles or the particle beams within the detector. This intersection happens 40 million times a second. So as you can imagine, it's a massive, massive amount of data. And when there is a beam crossing, you don't have just one collision. Right now we have, I think it's in the order of 60 collisions per beam crossing. In the next few years, we're going to ramp up the accelerator and improve some of the equipment that we have, and we're going to be at 500 collisions per event. So you can imagine that these numbers are going to go up. Okay, not the 40 million, that's the same, but the numbers will go up very fast. So with 100 million data points, 40 million times a second, we obviously cannot record all of this information. So we have a trigger system. The job of the trigger system is to filter down this data to something that we can actually manage. So it goes from 40 million events per second to 3,000 events per second, which is slightly more manageable. Most of the sub-detectors within a detector will have their own trigger system, and then there's a global trigger system for each detector. These numbers are for one specific trigger system, but it's to give you an idea of what they're like. So they usually set up the triggers in two levels. The first one is the hardware-based level 1 trigger. So these are all FPGAs, and they filter the incoming events to bring them down to 100,000 per second. They have really, really little time to do this. So basically what they need to do is start reading out the sensors from the detector and decide if the event that the sensors just picked up is something that is known physics and therefore not interesting and we can get rid of it, or if it's something weird that is potentially interesting and that we need to save. And they have so little time to figure this out that we have not even finished reading out all of the sensors of the detector before the level 1 trigger decides whether it's a good event or not. So that's how fast these things have to run. So after the level 1 trigger, we go to the software-based high-level trigger. So these are usually several racks of CPU and GPU nodes that are usually located inside the, not inside the experiment cavity, but underground in a parallel cavern. And these are just GPU nodes that are crunching the data, doing a little bit of reconstruction of the event to see if it's actually something that is worth recording or not. Since it's GPUs, they take a lot longer. They can do a more in-depth reconstruction. And then from here, they go to 3,000 events per second, roughly 6 gigabits per second. These numbers are, sorry, these numbers are kind of based on the trigger system for one of the experiments. It'll vary because some experiments have bigger events, so the rate may be higher. But this is finally where AlmaLinux starts to make a appearance. So CERN's journey with AlmaLinux kind of started with one of these experiments, with the CMS experiments. They started using AlmaLinux within their trigger farm, and then within the systems that come after the trigger farm. And they were the ones that told us that they were very happy with it, and part of the reason why we started to look at AlmaLinux. Okay, so once we read all of this data from the detector, the next step is to actually reconstruct what it is that happened inside the detector. So, okay, we don't use these actual pictures. These are just visualizations that are done after the fact, but it's to give you an idea of the complexity of the story. So what you get from the detector are a series of points where we saw something happened. Some energy was deposited. It's like if it was a pixel of a camera, there was a photon of light that went through it. So then you have to take all of these individual data points where something went through the detector and then try to do a track fitting algorithm to figure out if you have a hit here, one here, one here, one here, then it was probably a particle that went like this. This is relatively easy when you have one collision inside the detector. It becomes exponentially harder when you have 60, and in the future when we'll have 500, it means that event reconstruction is going to take a significant fraction of the CPU power that we have. So this, for example, is a reconstruction where there's one muon that was created. Muons are the ones that can go all the way through the detector. But you see that there's a lot of stuff going on here in the middle. So we do a lot of this reconstruction in the CPU farm that we have inside the data center in the main site. It's basically a batch cluster running HT Condor. We have about 5,400 servers, 422,000 cores, 1.6 petabytes of RAM, and a lot of that is running AlmaLinux as well. So once you've analyzed all of this data, or reconstructed this data, the next big task is that you have to store it. For storing this data, the first thing we have is a system called EOS. EOS is a home-built system that's developed at CERN. It's basically a disk cache for storing all the data that's coming in. It uses 115,000 hard drives and SSDs now. It's 310 petabytes worth of data. And on average, it handles, while the experiments are running, between 150 to 200 gigabytes per second being read in from the experiments and as well from the accelerator. And now this is just the cache storage. We also read from the system to do the reconstructions and to send it to the grid, which I'll talk about in a second. But our real storage is tape. There's no way that you can store all of this data on disks. It's just not economically feasible. So we use tape very extensively. For this, we have another home-built system called CTA, CERN Tape Archive. We are very good with names. So CTA stores 1.32 exabytes on tape. And this number, I was shocked when I looked it up the other day. It grew last year by 322 petabytes in 2025. I'm shocked because when I started at CERN, we always said the tape archive grows by 1 petabyte a year. But I was seeing the line and it's going ballistic, so it's really amazing. The machines that run EOS and CTA front ends are also running AlmaLinux. Now I mentioned that we also read the data out of the EOS cache, and the reason why we do that is because we send it as well to the worldwide LHC computing grid. So storing all of this data and processing all of this data is a really, really huge challenge, and we simply do not have the funding to be able to handle it. So many years ago, we decided to start the worldwide LHC computing grid, and it's basically a way to share the load of storing all the data with other centers and with other universities around the world that have a vested interest in actually using the data. So the grid is basically a tiered system where CERN is tier 0, and then we have about 14 tier 1 sites. Tier 1 sites are large centers in different countries around the world. The closest one is the one in, I think it's Karlsruhe, KIT. So the idea is when a physicist actually wants to process data, they tend to go to their tier 1 site that is more local, or to their tier 2 sites. Tier 2 sites are generally smaller universities, smaller data centers. They don't have tape storage, but they do provide disk storage and CPU storage. So all of the data that CERN stores is sent out to the tier 1 sites, and among all of them, they're supposed to store a second copy of all the data. So if anything happened at CERN and we lost all the tape libraries, we'd be able to recover most of that by copying data back from the tier 1 sites. This also reduces the network problem that we would have if all of the physicists tried to read everything from CERN when they're going to do mass reprocessing and things like this. So within the WLCG grid, we have currently around 1.3 million cores. We store 3.7 exabytes of data, and we have 150 data centers in 42 countries. I'm not going to say that all of them run AlmaLinux, but many of them do. Since these are independent data centers, then CERN has no say in what they run. They can just choose whatever. But many of these data centers did follow our lead when we migrated to AlmaLinux. So it's very good to see. So changing gears a bit, I wanted to give you a brief history of Linux at CERN. So we started using Linux. We migrated from mainframes and Unix machines around the year 2000. We started with Red Hat Linux 6.1. Then around 2004, we started doing our own rebuild of RHEL with Scientific Linux CERN. We were doing this in collaboration with Fermilab, which is another similar institute in the US. And this we kept up for RHEL 3, 4, 5, and 6. Then in 2015, we decided that it didn't make sense to continue trying to rebuild the entire OS when CentOS was already doing it. So what we did was we adopted CentOS, made a few tweaks on top, called it CERN CentOS 7, and we were very happy with that. In April 2020, we started putting CentOS Linux 8.1 in production. We skipped 8.0 because they're usually more delicate releases. And then in December 2020, as many of you, we were surprised with the CentOS project shift, where CentOS Linux was ended and CentOS Stream began. So this, of course, created quite a bit of waves within our community because people didn't know what we were going to do. We had been using RHEL-based systems for 20 years, so we were pretty tied in. So at first, we evaluated the options, and we decided that what made sense was to, okay, let's take Red Hat at their word, and let's move to CentOS Stream. So we were using CentOS Stream for a while, but it soon became a little too delicate. There were too many changes too quickly. Physicists do not like changes, especially quick changes, mostly because so when they run an analysis, they want to make sure that if they run it next week, it gives the same results, and which is fair enough. And the problem is that with CentOS Stream, we had many changes to very core components like GCC or glibc and things like this, and these changes do affect physics results when you're talking about like very crazy decimals. So after roughly a year of running CentOS Stream, we started to realize that we needed to move to something else. And then this is when we decided to move to AlmaLinux. So how did we decide? So we spent some time looking at all of the alternatives, also trying to consider if there were ways that we could change our way of working to accommodate the CentOS Stream lifecycle. But eventually we decided that we needed to move to AlmaLinux. And the reasons were some of the ones that Andrew already mentioned. So the AlmaLinux team has a great community relations with Red Hat. They're very well integrated. They participate with the wider community, provide Elevate, another open source tooling that helps everyone. The governance of the project was very good. We really liked the fact that it couldn't be taken over by a company or an individual, that you couldn't have a repeat of the situation with CentOS, for example. This was something that was very important to us. We also liked the fact that they had full errata support basically from day one, which is something that some other competitors can't say yet. We also looked for a couple of months at the speed of releases of updates, both for CVEs and miners releases, and they were very, very fast. So this was also something that was very encouraging. And the most important thing for us was the stability and long-term support. So this is so important that I wanted to share a different slide just about this. So I don't know if I've managed to communicate this yet, but CERN does not think in years or quarters or anything like this. CERN thinks in decades. So this is a snapshot of the long-term schedule for the LHC. In the green sections here, this part is what we call a run. This is when the experiment is actually running. During the end of the year, it's shut down for roughly a month because they can do some very small kinds of maintenance operations during this time. And then after every run, we have a long shutdown period. So we are about to start a long shutdown 3 now. Within a long shutdown is when they make major changes, where they replace entire subdetectors, where they replace magnets that are slightly damaged, where they can do major upgrades like change the operating system. During a run, if you tell anybody in the experiment control group that you want to change the major OS, they will kick you out of the room immediately. You do not screw around within a run. You have to wait until a long shutdown. This is why for many of the experiments, we are still supporting CentOS 7 because they are still running stuff in CentOS 7, and during the run, you do not touch that. So gotta wait until the long shutdown. So the fact that AlmaLinux gives us 10-year life cycle, even though it doesn't necessarily line up with our schedule, it gives us a lot more flexibility and a lot more options. We would not be able to do this if we were running CentOS Stream, because then you would have changes all the time in here, and this would just be chaos. And to hammer the point home of how we think in decades, this is the plan for the future of CERN, the Future Circular Collider. This is something that we've been working on for several years now on the plans. Our plan is to build a much larger accelerator, 90.7 kilometers in circumference. So you see the LHC here is tiny compared to it. It's going to be between 180 and 400 meters underground. There's another collaboration that is forming to get this off the ground. It's currently 150 institutes in 30 countries. Part of the problem is that this project is so popular that people don't want to work on the current stuff now. But the research project for this, so the research program is 70 years. So we just published the feasibility study last year. This is a huge report explaining all of the details of how the machine would be built, where it would be built, what technologies need to be invented, because none of the technologies exist yet to make this possible. In 2028, the member states are supposed to decide if we go forward with this plan. If they do, we would start construction in 2030, would not start operation until the mid-2040s, and then it would be running for 15 years. Then we would take roughly another 10 years to upgrade this accelerator to a machine. So the first one is a machine capable of colliding electrons and positrons, and then we would upgrade it to one capable of colliding protons, which is what the LHC does now. The LHC itself was preceded by another machine that collided electrons and anti-electrons. So you can imagine that when you have plans that span 70 years, you really care about the stability of the operating system because it is a very critical base. So this is why, once we decided that we were going to use AlmaLinux, why I joined the board, because part of my job as a member of personnel for CERN is to think about this and make sure that we still have an AlmaLinux that we can use in 70 years. So that's it for me. If you have any questions.
All right. Thanks, Alex. So I guess no questions.
Oh, there's one.
There's one? Yeah, there's a mic there. You can answer if you will. Good, sir. Thanks, Jonathan.
I'm coming here.
That's Tom and Jerry right there.
Hi. My question is not regarding AlmaLinux, but regarding the really long plan to build underneath the ground. Why is it better if it is longer? It's impressive, of course, but there are other reasons, I guess, physical reasons.
Yeah, the reason why it's so large is because you want to use very high energies. You want to get even closer to the speed of light. And in order to do that, you have to either have extremely powerful magnets that are capable of bending the beam quickly enough, or a really large accelerator. So it's always a trade-off between, can you invent technology that is powerful enough to bend the magnet small so you don't have to dig as much, or do you just dig bigger so that you don't have to have extremely powerful magnets? That's why it has to be so big.
Thank you. And the other question is more regarding AlmaLinux again. So would you also recommend AlmaLinux for OT environments? Because also OTs have this really long, really long periods of using technology, operating systems, and devices.
Yeah, obviously it's better to have an operating system that gives you 10-year life cycle than one that gives you less, because that means you have to do fewer upgrades and you have fewer worries, and more importantly, more time to plan the upgrades that you do need to do. So it's easier to find a point in time where the business allows you to do the upgrade.
Thank you very much.
There's another question right there, yeah. I mean,
Oh, yeah, okay. I have another question. I noticed the
Sorry, I need
switch
two
from CentOS Stream was rather close to the next run of the LHC. So was it a hasty decision to go to Rocky then, or was it planned?
What?
No.
No, because the experiments, when they started the run, they were already using CentOS 7. So at that point, it didn't matter what we decided. They were not going to migrate until the long shutdown. The question is, we have to be ready by the long shutdown. They want to be ready 2 years before. They want to know exactly what OS you're going to, because they have to start changing their stuff as well. Yeah, and also not, even when the long shutdown happens, not everybody can migrate immediately, because, for example, the cryogenic systems, they can't just shut them down the day of the long shutdown. They stay on for quite some time, there's some variation. So even during the long shutdown, you don't have total flexibility to change whatever you want. But this is why we look at these things very, very far in advance, because we need to plan ahead, make sure that the operating system, all of the build tooling, all of the other infrastructure that the experiment people need is ready before they have to start making the switch.
Hello, the number is really impressive. My question is about the storage. How long does it take to save a second copy from the data to the tier data centers? Or if some node of the tier data center is going down or so on, how long does the restart take? So theoretical, I don't know if you tested.
We've never tested a restore. That would be...
Thanks. Thank you very much.
Yes. Yeah. So I don't know exactly how long it takes to transfer a day's worth of data. I think it's less than a day. So the bandwidth that we have with the tier 1 sites is very, very good.
Just another question about the topic of CloudFest. Did you use also AI?
In the production of these slides, no. We do use AI relatively heavily. So not the generative AI, but a lot of particle physics is done using neural networks and so on from years and years ago, before anybody called it AI. So now they're kind of trying to rebrand it so that we seem cool again.
One question regarding the new project of the large new Hadron Collider. What's your main hope? What you will gain out of it? What's your hoped value at the end of the day?
So that's a very difficult question for me to answer, because this goes into the physics of the whole thing. At the end of the day, the hope is to have higher precision measurements of some of the things that we already know that exist, and to start looking at things that we don't know necessarily where they exist, potential future particles, but also things like the matter-antimatter asymmetry, which I mentioned before, why we have only matter around us, for example. Dark matter is also something that we want to study. The hope with the FCC-EE machine is that the collisions it's going to provide are a lot cleaner. You saw the image of the reconstruction. That is a lot of lines in the middle. It's very difficult to see anything. When it's anti-electron collisions, they are super, super clean, and it's very easy to see physics without a lot of background noise. So a larger machine gives you the possibility to create higher energy collisions, which gives you more potential for creating bigger particles within the collision. And that's why they want to increase the energy, basically.
Okay, thank you. And the second question is, did you think about the implications on the infrastructure that it would need for this much larger?
This is what us in IT always ask the physicists. Who's going to think of the infrastructure? So we do a lot of planning to see whether we're going to be able to buy enough hardware to accommodate this sort of growth. We used to see about a 15% increase per year in performance, both CPU and storage-wise. That number has gone down to 10% a year. And there are serious concerns that it may not actually be feasible to store all of this data, because hard drive prices go through the roof. Memory is no longer available. It becomes a very challenging budgetary problem, because we may not have the infrastructure capable of storing all of the output from these machines. The good news, in parentheses of this, is that we have time. So who knows what's going to happen in about 20 years. Also, you have the trigger system, which is basically a dial that you can turn. If you can't store enough data, you make the trigger more restrictive, let less data through, and that's good. The physicists are not happy because it takes them longer to have sufficient statistics for their analysis, but it's better than nothing.
Thank you very much.
You're welcome.
Hi. One technical question. What kind of tapes you're using? So when you have nearly 1 petabyte of data every day, so it's very high load for tapes.
Yeah. So we have IBM tape libraries and we have LTO tape libraries as well. I don't remember how many tape libraries we have, but it's a pretty large number.
Are you delete some data sometime, or it's
No.
stored forever?
Not on purpose, at least. So we store all of the data, including all of the data from previous experiments. For LEP, the previous experiment before the LHC, we still have all of the data. Luckily, technology improves, so all of the LEP data for the entire run of that accelerator fits in, I think it was like 20 tapes of the sizes we have now. But we store absolutely everything. And actually, data preservation is a major issue because now we have physicists that, since the newer machine, FCCEE, is very similar to the LEP machine in terms of the physics, what they want is to be able to recover the LEP data and reanalyze it with the tools that we have now. They've been doing this. They've found some interesting physics that we didn't have the compute capacity to study back then. Now suddenly we do. But it also means that you have to make sure that the data is still readable, that you still have the knowledge and the metadata and so on to know where the data is, how it's structured, how to rerun the analysis that were all written in Fortran 77 and so on. This is another thing why long support on distros is very useful, because then you can still run the old analysis code for quite some time.
Okay, one short personal question. How does it feel for you? So think in decades, and so for us, usually you have thinking about 3 or 5 years. So, and you were thinking about decades and time, maybe after your life. So
Yeah, that's a good question. On one hand, it's very exciting because you know that you're participating in something that you are not going to be alive to see the end of it, and that there will be other people that will be taking over, and that you're just one small part of a very, very large project. That's very rewarding. On the other hand, it's exhausting because you finish the migration to RHEL 10 and suddenly you're thinking, oh, okay, RHEL 11, when is that going to drop? How am I going to do that? Then should we skip 11 and go to 12 directly? And it gets a bit much at times as well.
One last follow-up question from my side regarding the memory issues we have with the prices, etc., etc. Did you think about maybe some point of manufacturing yourself memory or building up? I mean, I guess it's a break-even question. You know, how expensive do the memory chips need to be in order to take the decision? Because you use much memory, so I mean, yeah.
Almost every last cent that we get goes to physics. There's no way they're going to let us set up a chip fab. Yeah. Yeah. This one? Or fine.
I have a small question. You have been within the infrastructure with, that I already thought it was up. I will restart the question. Do you have seen in the recent time when the AI hype that the usage of neural networks has increased within your infrastructure or other forms of machine learning?
Yes and no. So for actual physics work, they've been using neural networks for ages. Even within the trigger system, they've been using neural networks a lot. There are newer projects now to use newer types of neural networks and newer technologies, and that is changing a bit the infrastructure that we have to provide. There are a lot more people that are interested in doing AI-assisted research or things like this, but that doesn't really move the needle that much compared to all of the other compute that we have going on.